Hello, everyone, and welcome to AWCI's webinar, How Cold-Formed Steel is Shaping the Future of Data Centers. My name is Tawen, AWCI's Education Program Manager. At this time, I'd like to introduce our presenter, Andrew Newland. Andrew has 15 years of experience in both cold-formed steel manufacturing and design, including nearly 10 years of experience designing cold-formed steel framing and components in data centers. He is a principal at ADTEK Engineers, Inc. and the Specialty Structural Team Leader for the Maryland, Michigan, and Virginia offices, which all specialize in the design of load-bearing and non-load-bearing cold-formed steel projects. So welcome, Andrew.
Thank you. All right, so today, as Tal mentioned, I'm gonna speak about how cold-formed steel is helping shape the future in data centers. So this presentation is copyrighted, so can't be reproduced without our knowledge. So learning objectives, today we're going to speak about what a data center is and where they're built. Then I'll go over some typical exterior framing in data centers, then discuss interior structural and non-structural framing, and then we'll finish up with structural ceilings and hot aisle containment. So to start off, what is a data center, other than just a big nondescript box? So a data center is a physical location that stores computing machines and the related hardware equipment. It contains the computing infrastructure that IT systems require, such as servers, data storage drives, and network equipment. It's the physical facility that stores any company's digital data. So now there's a number of different types of data centers. There's network infrastructure, which connects servers, data center services, storage, and external connectivity to end user locations. Storage infrastructure, that's where physical data is stored, and then computing resources. So those can have servers, which provide processing, memory, local storage, and network connectivity for applications. And within those different types of data centers, there's a number of different tiers. And typically, they are broken into 4 different tiers. So tier, and it's based on the amount of protection that is required within them and how much interruption they're typically allowed to have. So tier 1 would be a basic type data center, which would have the least amount of protection associated with it, all the way up to tier 4, which is a fault tolerant data center, which would have the highest levels of fault tolerance and redundancy. I think this all kind of comes into play when you're thinking about what happened a couple of weeks ago when we had some major interruptions in number of services. So theoretically, that type of interruption should be relatively limited, and there's a number of ways that they kind of protect around that, and that kind of plays into where data centers are being built. So I've done a couple of these types of presentations here recently. So in 2024, I found this map from datacentermap.com and /USA. You can actually look at where they're also built across the world as well. So this map was from 2024 that I put into a presentation. And within a year, you can kind of see the numbers have really kind of skyrocketed. So I'm here in Virginia. We've had more than over 100 data centers, close to 200 data centers added in Virginia alone. And there's also a number of different hot areas across the United States where they're also being, the number of data centers is growing pretty much exponentially. And so there's some reasons behind the growth. The global demand could more than triple by 2030, and that includes 25% growth in the United States alone. About 70% of that growth could come from hyperscalers. And so what a hyperscaler is data center builders who are producing large campuses and putting a number of data centers in a single campus to kind of maximize a location and the construction there. So, and demand's creating capacity challenges for these primary markets. So there's obviously both water and electrical concerns. So that's kind of driving different locations, the addition of locations, and where exactly they're being built and how they're being built. So depending on where you look, there's a number of different ways they kind of indicate what the biggest markets are. Kind of consistently, Northern Virginia is the biggest market. It's also still one of the fastest growing. There are a number of other fast growing markets, including Las Vegas and Phoenix. Texas is also a fast growing market, but these are typically the top markets in the United States. And there's a number of different reasons behind that. So Virginia, Northern Virginia and Virginia specifically, one of the main drivers is our low natural disaster risk here in Virginia. And so that kind of ties back to that limited fault interruption that they want. So they like an area with a low natural disaster risk because then you don't have to contend with any kind of seismic and potential for interrupting connectivity. Also, our proximity to Washington, D.C., energy access, and tax breaks. Now, tax breaks are something that's kind of occurring across the country as different locations try to get more data centers built in their areas. Dallas is another area that's located between Washington, D.C. and California, so it's kind of a midway point. There's some other areas as well that have that same benefit. It has low real estate costs for data center markets. Silicon Valley has robust connectivity. It's an innovation hub. Similarly, Los Angeles, the New York tri-state area, it's needed for ultra low latency there. So with our financial markets and everything up in that area, that's the reason why a number of data centers are being built there. And also similar, they have a low natural disaster risk there as well. In Chicago, it's again kind of that midway between the East and West Coast. Low energy costs and tax incentives. Washington, D.C. provides low latency for government agencies. In Atlanta, there's a high concentration of large companies, Fortune 500 companies. They have competitive energy costs and a low natural disaster risk. Miami has our gateway to Latin America, the Caribbean, and Europe. There's the subsea cabling with South America, good transportation for infrastructure. And then finally, Phoenix has affordable energy, low taxes, and again, minimal natural disaster risks. And with these benefits, each kind of has their downsides as well. But there's definitely everywhere in our country has a number of growing markets for data centers. And the data center market is still continuing to grow. It's a very large market and one that continues to get bigger and bigger in our country in a number of different areas. So now that we've kind of talked about what they are and where they're being built, I'll talk a little bit about what makes some exterior framing unique, and then I'll run through some typical exterior details. So some unique aspects of exterior framing in data centers. Data centers typically have very long spans. As a lot of you probably have seen as you've driven in various areas and seen data centers, they're just kind of nondescript boxes. So a lot of times cold form steel is used for metal panel support, whether it's connected to precast or tilt-up walls, and then also different kind of canopies connected to the same precast or tilt-up, or even cold form steel walls as well. So for when I say that they have long spans, a lot of times you'll see greater than 20-foot slab to slab heights. This will also affect the interior framing, whether it's structural or non-structural. Often have large parapet heights, kind of used as kind of screen walls for roof equipment. So parapets up to 15 feet tall in some instances. And then you often have large openings, so long spans above openings that typically require kickers and rigid framing. So when you're dealing with that type of connection framing, the curtain wall should be able to accommodate the differential deflection in the floors. So, and then there's some reasons for the large floor-to-floor spans. One big reason is cooling. Obviously, all the servers that are located inside these buildings create quite a bit of heat, and that's something that they are continually trying to contend with. So the large spaces help with the cooling. So that's one big reason for the large fans. It also provides an option for future expansion. Depending on how they are installing their equipment, whether it's below they have a raised floor that they have their cables and whatnot running below, or if it's a hung ceiling, it provides an option for installation and maintenance. And that, also with the raised floor access, they have cable management, and that helps with cooling, expansion, and maintenance there as well. So I just kind of wanted to highlight a few details that we've seen with some of these long spans. So in this instance, we have a 14-foot tall parapet and then a 19-foot floor-to-floor height. And then some other areas where it's large kicker framing that's required. We're connecting to post-tension concrete with kickers and fixed clips to make the framing work in these instances. And then that other one, you have multiple long spans where you have to create a splice in the middle of the wall to be able to make it work. And then the final two, kind of those canopies, as well as large kickers at the roof and above the curtain wall to make the framing feasible for the situation. So for metal panel support, most data centers that we're seeing, so I showed some pictures where there was quite a bit of framing and it was less so of this, but most data centers are either precast or tilt panels. And then CFS is kind of used to more as an architectural feature to kind of for these otherwise unsightly just precast buildings, they put metal panel on it to kind of pretty them up a little bit. They're often used at stairwells and for signage support. So with this, your connections to precast can create a number of different challenges. And then as in the previous pictures, some of those shells do contain significantly more CFS. So with some of the connections, you have to note whether PFs are permitted or not, or if you have insulated concrete panels, you need to consider whether the first panel is the thinner one or if it's the inner one that's the thinner one, because then you're kind of limited on the type deep embed anchors you can use. You might be pushed to using an expansion type anchor or a adhesive type anchor instead of an expansion or screw anchor to make your connections work. So, and then these are some of those typical details that we're seeing with the metal panel connections that are going to precast or to the tilt panel. So in the middle there, that's kind of where I was talking, you have that thinner outer concrete layer and then the insulation. So with this, we had a canopy that we couldn't feasibly make the connection work with a shallow type anchor due to limitations of the concrete. So we had to use a deeper anchor with an adhesive that went all the way through to the thicker portion of the concrete. But these are common type details that we're using on a number of data centers here in the Mid-Atlantic market. For exterior canopies, a lot of times they're similar to other type canopies and soffits on other projects that are not necessarily data center projects, but we do commonly see these type of details. So just large canopies to kind of make it a little bit prettier of a project. Then, canopies typically over doors, like the one on the right. And luckily that one wasn't the insulated panel where we could have an easier time making the connections work for that. And then some other common exterior conditions that we see. There's often expansion joints at the roof. So with this, we need to make sure that we have proper bearing for our connections. If it's sitting on metal deck, that can be a little bit difficult making rigid connections work with cold form steel. But this is common due to the size of these buildings. You often have roof expansion joints. And also we commonly see expansion joints between a new and existing roof as well, when they add on to an existing building, or they build one phase of the building and then have to add another portion as well. So onto the interior framing portion. So as we're seeing more frequently, not just in data centers, it's a common question of whether or not I need to get it engineered. So in a lot of times, it depends on what the spec says. Sometimes you can use limiting height tables, but you need to make sure that you're using the right pressure. So for data centers, your pressures can be wildly different. It's not always the standard 5 PSF that you're used to with interior framing. We often see 10, 15, and even 20 pounds per square foot for an interior pressure. So when you're looking at interior framing in a data center, you a lot of times get outside the realm of when you're allowed to use non-structural framing and when you're forced to use structural. So when does it need to be engineered? So if you have tall walls with a high interior pressure, there's plenum corridors. So it's kind of areas where they're pumping air through that, again, have those higher pressures and sometimes some weird configurations to them. There's a number of data centers that use what's called common supply headers in their adjacent walls. So this is another area where they're pumping high pressured air through, and this is all part of the cooling process for the data centers to kind of help keep them cool. There's often large louver headers that require engineering and some different interior features that are included in the data centers, just so it's not just all kind of an industrial feel inside. So plenum corridors, so these are some typical details that we see for a typical type data center here. So these typically have that higher pressure, up to 20 pounds per square foot, that we need to design for. The ceiling may be walkable at times or have a live lid that's required to be placed on the framing. So they have multiple beams and posts are required to frame this all out. There's long spans and some rigid framing. So this is not like a standard bulkhead that you would see in a normal type building. This is definitely a bit more complex, and this is the type of framing that definitely needs engineered, and you need to contact an engineer. I mentioned that common supply header and the Dahu walls. So what we typically see here, there's typically two types. There's either a double full height wall, or there's one partial wall with a walkable ceiling. And with that, you also have a guardrail. Your shorter wall that's not full height will have a guardrail that needs to be accounted for. And with this, what they do, we often see multiple loading conditions for this. So it's not just the standard 5 PSF interior pressure. What we're often given is your IBC of 5 PSF interior pressure, a service pressure, and then your extreme pressure. And so what this typically is again, the 5 PSF. The service pressure is what the anticipated pressure is being pushed through, and then the extreme pressure is a pressure that is the absolute maximum that the system could possibly put through. There may be some additional hung loading requirements that need to be accounted for, and then also a seismic weight on the ceiling as well. So, and when we're looking at these are typical loading diagrams for this type of wall framing. So basically, when we're doing our engineering, we have to kind of go through an iterative process with this and check multiple different conditions, and you also have openings in it often, which then further complicate the design of it as well. But so, as I mentioned, you see the 5 PSF IBC load, your extreme pressure that you have in the middle, and then your service pressure. And so this is kind of just going through the typical design of it. And then one thing I didn't mention is, so they also give some maximum deflection. So typically it's either L over 240 or less than 1.5 inches of deflection for the IBC, and then L over 60 or 1 inch for the service pressure. And that's just to limit the deflection for the normal cases. And then for the extreme pressure, they just want it to be designed for strength. They're not too worried about deflection. If the maximum situation happens, it is more of a worst case scenario that they don't expect, but want to be accounted for strength wise. And then repairs can be taken if need be at that point. So kind of going through, this is just a typical design process where you have your 50 PLF guardrail load. You design the outer member for each of those conditions. It applies a load on your full height wall. You have your joist member as well. And then one thing to consider when you have both your extreme pressure and your service pressure, to an extent, they're acting in equal and opposite directions. So you technically are supported for those higher pressures at the joist location, because they're pushing out with the wind that's being pumped through the corridor there. And then with that same design, you'll have multiple louver openings that need to be designed similarly with those various pressures, the IBC pressure, service pressure, and then extreme pressure. So all your header members, GM cells get designed for those, above and below the joist member, the ceiling member there. So it becomes kind of an iterative process doing your design for all these different members. So another typical thing that needs to be designed when you have large interior louvers or interior metal panel walls. So often there's headers and jams aren't always necessarily feasible for some of these. You have a 30-foot tall wall height, and then sometimes you might have a 20 to 30-foot header. So typically that's not going to be something that's feasible. So you'll have a rigid stud with a kicker, and we've been often requested to put a slotted deflection track at the bottom to allow for the movement, so that the metal panel support and design at the bottom shown there doesn't need to account for the vertical deflection. So that's the detail we've used at the bottom there. And then this is a picture of one of those type situations where we have a large wall that has that, it's a very tall wall that has that large wide opening. So we provide the kicker support there and deflection at the top. So some other interior features that we've engineered, and I'm sure there's definitely more type features in various different data centers. There's a thing that we've seen called a shard wall, which is kind of like a decorative wall, a freedom wall, which carries a giant American flag in it, and then various different type monitor walls, just supporting large monitors, which is kind of typical of a lot of interior framing, especially when you have tall walls that have heavy monitors on it, has to be supported. So now on to structural ceilings. So there's a number of different things to discuss. There's whether it's a strut ceiling or a proprietary system supported by strut, or the structure itself. I'll talk a little bit about the various different strut members, different grid spacings and loadings, the typical structural support, and then we'll talk a little bit about seismic as well. So the different types, you have either a proprietary structural ceiling system, so that could be like Orden, Tate, Polar G, there's some others out there. So that system is either hung from an interstitial strut that's supported by the structure, or the ceiling itself is just directly supported from the structure. Some of the loading requirements for the project may be too high for these systems. And so when that happens, then you have to get into a strut ceiling system. And so then that strut ceiling system, again, is typically hung from the structure or maybe needed to be hung from an interstitial strut as well. So and then these are just some different pictures of some different systems. So I think on the right there, that's a proprietary system that's directly hung from the structure. In the middle, kind of have that strut system that's hung. So just some different type ceiling systems. And then this is what they typically look like after they close it all up. So they put ceiling panels in it. So, and what they do, whether it's the proprietary system or a strut system, your grid allows for them to then hang from, with the ceiling in place, hang directly from the strut or structural ceiling to hang cable trays and support cables and wires and electrical and various other things. So for the strut members themselves, there's some very common configurations. Different manufacturers have a lot of different nomenclature, and it's kind of all over the map. What the nomenclature means and how it's laid out. There's single or welded back-to-back. There's also some additional less typical configurations available, but those aren't typically used for the structural ceilings. Get used somewhat for the hot aisle containment that I'll mention a little bit. They come in various depths and either slotted versus unslotted. And when you're dealing with the slotted, you have a strength reduction in the slotted. So there are differences in the different manufacturers. So if an engineer is designing using one manufacturer, they're not necessarily all equal. So if you substitute without telling your engineer, then they may not have designed the appropriate strut. So you would need to run that by your engineer to make sure that the strut that you're actually using meets the requirements that are specified. So, and we've seen that depending on the manufacturer, they have widely varying lead times. So it's important, definitely important to bring that up with your engineer. So these are a number of different manufacturers that we see here in our market. There's Unistrut's kind of the band-aid of strut. They're just pretty much the generic. And then there's a number of others that follow the same dimensional, same dimensions that Unistrut has, but again, they have different capacities listed for their specific strut. So, and also the nomenclatures are kind of all over the map here, but what you're looking at, the typical base strut is going to be 1 5/8 by 1 5/8. Then, as I mentioned, they have the welded back-to-back. Then it goes a little bit deeper to 2 7/16. They do that back-to-back, and then 3 1/4 with the 3 1/4 back-to-back. And then typically any of these come in a slotted. So the slotted has some different nomenclature depending on who the manufacturer is. And slotted, we've seen from data center to data center. Slotted may or may not be required. Sometimes it's a requirement, sometimes it's not permitted. So it's just that's something also to look out for, whether or not it's permitted or required, because it affects connections, whether you have slotted or unslotted, and it affects the capacity of the strut as well. And then also another manufacturer is Hilti. They also have they have a strut member as well that has slightly different sizes than what the typical strut members have. And so for the grid spacings themselves, there's definitely a number of different spacings. So some typical ones, and you'll either find this in the spec or the architectural plans, are 2x4, 4x4, all the way up to an 8x8. And typically when you're looking at the 8x8, it comes out to 8 foot 1 5/8 by 8 foot 1 5/8. And so that allows for the panels themselves that fit within the ceiling system to actually be 8 by 8. And the extra 1 5/8 is to account for the strut member themselves. So when you're loading for these, they're found in a number of different places. It could be the specs, the architectural plans, or structural loading plans. And they're often listed as a max point load, max PLF, or max PSF. Sometimes you have multiple, you need to account for multiple of those as well. So, and as far as the specs, where they can be found, we've seen them in a number of different places. Slotted channel framing spec, metal fabrications spec, the structural ceiling grid spec. So it can be found in pretty much any of these possible locations. So, and if you look at this is a screenshot from one of the specs, they give a couple of different things. So they give that max PSF load, so that for this one, it's a max 50 PSF that you need to design for. Also, an ultimate point load of 700 pounds, and then the turnbuckle, which typically is beneath the structure above the ceiling, needs to be designed for 800 pounds. So often what we see with these ceilings is they want the large grids and also want high uniform loads on them. This 50 PSF number that I have here is almost becoming outdated. We've often started to see even higher uniform load requirements, 60, 75 PSF in some situations, even up to 100 PSF. So when you get up to 100, these large grids aren't necessarily feasible, but we've definitely seen much higher uniform load requirements than even 50 PSF now. So when you're looking at these large grids and kind of that 50 to 60 PSF, which is still feasible, your strut, you need to make sure that you're checking the brace members as well, because depending on the loading conditions, they may need an addition. You may need to add some additional bracing to make those work. Another thing to consider is if you have large beam spacing without the permission to connect to slab, or if you're at the roof level and you don't have a slab to connect to, then this can make the design of some of your framing, your strut framing, relatively difficult. So now, what are they exactly connected to? There's a number of different situations. So existing buildings are becoming less frequent just because they're building almost exhausted a lot of them and kind of building new more frequently. But when you have an existing building, you have existing concrete you need to contend with, or bar joists. Other type buildings are steel beams with composite concrete at lower floors. Sometimes you have concrete at the roof, but often it's metal roof deck at the upper floors. And then a precast tees with embedded strut is another common connection. So for that existing building condition, if it's concrete, then you'll need to verify the capacity of the concrete. Typically, you'll have to get a manufacturer out there to do some pull tests for some of your connections, just to ensure that the connection that you're designing is actually sufficient. Bar joists, there's a number of ways that you can connect a bar joist, similar to typical steel connections. Alternatively, you can use through bolts between the cords, those beam clamps. One thing you need to be careful of, and we also see bar joists in new construction as well, but the panel point connections, typically it's somewhere between 1 foot to 6 foot within a panel point. You need to make those connections, so that can kind of present some coordination issues that just need to be careful of. In some where we've done some projects recently where to avoid the coordination, the contractor just ran a continuous strut beneath, parallel with the bar joist, and then hung from the strut. So they were able to keep their connections within close to the panel points and drop directly from that strut wherever they needed to. So for a new type building where you have steel beams, one thing you need to check is if you can connect to the slab. Some some projects you're not permitted to connect to the slab, so you have to go directly to steel. There's a number of different ways to do that. So common way is the U-type clamp. So you have strut tight to the beam, and that can be single, double, or a deep strut. And you need to size your U-clamp specifically for that. We also see these often required because the C-type clamps on the bottom left there aren't necessarily permitted because the EOR doesn't want there to be any kind of offset loading on the flange. So they want to limit the amount that you would be pulling on a single flange. When you're designing those C-type clamps though, you need to make sure that you're looking at the actual beam size, because the flange size of the steel beam is going to affect what type clamp is permitted. The manufacturers have some different requirements. If you've a large clamp that's required, then you might need to use kind of this piece that's the retainer strap shown on the bottom there to be allowed to use that larger type clamp. And then finally, this is relatively new that Hilti came out with, so they have a welded rod that gets directly welded to the underside of a steel beam, and then rod is able to be hung directly from that. So when you have precast tees, so these connections are most exclusively to the embed strut, which is going to be designed by the SEOR, the precast engineer. They may have some match reactions that are permitted to the embed strut, and when they do, they need to indicate what those are. You're also, in this case, limited by your spring nut capacity, so you may have to increase your rod size in this case, where you would have been able to use a smaller rod, but because you were using a spring nut or a channel nut, you need to increase your rod size to accommodate that. There are some other connections that may be permissible in certain situations. Where we've had some interruptions in the embed strut, we've been permitted to connect to the sides of the precast tees, but that they typically have, the precast engineers have some specific parameters associated with that, where you're allowed to connect, how deep you're allowed to connect. They've also permitted the use of their precast tee pick points as some through bolt locations, which we've utilized in the past as well. And often another thing that needs to be accounted for is trapezing around your precast and post-tension beams, because those have so much post-tensioning in them that you really can't connect to them, so you need to frame around them. So, and as I mentioned with those channel nuts, so in this case, if you had a 50 PSF load, your precast tees are spaced 6 foot on center and you have an 8 foot grid, you end up with 2,400 pound reaction. So where the rod itself would be fine, typically with a 1/2 inch, because of the channel nut capacity, you need to go up to a 5/8 inch diameter in that case. And then another thing to consider is your wall connections. So typically you'll have a rod drop close to a wall, so you can utilize just kind of tying the end of your strut to the wall without any kind of load carrying capacity. But if a load carrying capacity is required out of it, you would have to do something more closely to what's on the right, where the wall is actually carrying the load. So kind of wanted to go through just a quick example of designing a ceiling. So in this case, we have a 50 pound per square foot load with that 8 foot plus by 8 foot plus grid. In this case, we have a W16 by 31, so that has a flange thickness of less than a 1/2 inch. And our steel beam spacing 7'9" on center, so that's actually a pretty common one that we see. The connections to slab in this case aren't permitted, and we have an L over 240 deflection limit. So our first member that we're going to check is our brace member. So if we have our 8 foot inch and 5/8 by 8 foot, inch and 5/8. So our brace member would be the one that's spanning. We have some continuous members, and then we have members spanning just 8 feet between the other struts. So with that, we end up with 407 PLF for our uniform load. So that's the actual what we need. This number is what we need to design the actual strut for. So if we go and look up the unbraced capacity, so our member is 8 foot long, but we don't have enough capacity out of it, so we have to add some additional bracing to that member. So to get that, we'll have to add mid-span bracing to our brace member. So then for your continuous member, so these ones typically will be 20-foot long sticks of strut. That's what they typically sell in. So we have the same 407 PLF. This one's running continuous between the members. So at every single steel beam, you're dropping directly from the steel beam. So in this case, we have a little bit of relief on our design. So we're able to get, it works at the 8 foot bracing. So, however, we do need to make sure that we are splicing it with a moment splice. And so doing that, if for the manufacturers, as long as you're filling the holes and using their splices, then it works as a full moment splice. So then as far as the reactions, so we end up with approximately 3,600 pounds. So looking at the table for our clamps, in this case, a 5/8 would be required, but to get 3,600 pounds, we need to use 2 5/8 inch clamps to make this work. None of the single ones have a design load that meets the requirements. So in this case, we provide a detail clamping, having 2 clamps on each side and dropping 2 rods. And similarly with the U-type clamps, those typically have a capacity of about 1,000 pounds. So in this case, those also would not have enough capacity. So you'd still be required to do the 2C clamp with the 2 rod drop in this case. So, and then as far as seismic goes, so as I mentioned, I'm located here in Virginia. Virginia has the benefit of being a low seismic area, which is why they're frequently built here and we are the data center hub. But there's definitely other areas of the country where they are in higher seismic areas, you know, obviously California, South Carolina, and a number of other areas that do have a higher seismic category than what we have here. So you definitely need to check your seismic design category in your drawings. If it's seismic design category A, it may not be necessary to provide seismic design or seismic restraint for your ceiling. However, there are cases where the SEOR and owner may still require it. So you definitely want to read the structural general notes and details and specifications to see whether or not seismic is going to be required, because that would be something that you would need to include. So when we're doing the seismic design, we're going at a ASC 7. This is from ASC 716. As we kind of get to 722, the design's going to change a little bit, but this is the basic parameters around the seismic design. And then so detailing wise, it's going to be detailed 1 of 2 ways. Technically 1 of 3 ways. So if we have those precast tees, all the bracing, seismic bracing is going to be using strut members, going from your strut to strut with some rod and some diagonal struts as well. If you have either a concrete slab or steel beams, I said 3, I'm only showing 2. The other option for the one on the right would be connecting directly to steel. So you'd be using typically 9 gauge or even 12 gauge wire, depending on the seismic requirements. But so it'd be 4-way wire, and that would be what you would use to restrain seismic in that case. So then some additional strut designs. There's hot oil containment. So it's what that is. It's an area that contains the hot air. So exactly what it says. And so strut is often used around that as well. Electrical busway support, which is typically designed by the electrician. Cable tray support, typically designed by the whoever's installing that. So those are just other places where strut's often used as well. So with your hot aisle containment, typically it's some limited loading, typically 5 PSF. There'll be, may have some light busway and cable tray support required as well. So some additional limited support, but typically the loading is relatively light. And these are typically supported directly from that structural ceiling that I showed you some pictures of earlier in the presentation. So you need to ensure your connections are applicable to proprietary systems. Most of the proprietary ceiling systems only accept 3/8-inch diameter bolts, so that's just something to consider when installing and designing them. So and this is what the typical hot aisle containment would look like. You would have your, in the center there, you would have your hot aisle containment installed underneath. There'd be some screens that would be attached to the strut, and then the other cable tray strut supported off it as well. So kind of brings us to the end. So hopefully we now know what a data center is and where and why they're built. Some different typical exterior framing, about interior structural and non-structural framing, and all about structural ceilings and hot aisle containment. So with that, I'll conclude and open it to any questions.
Thank you, Andrew. A couple questions coming in here. So on slide 28 for stud 2, do we need to specify the deflection clip at the top of the stud due to loads from the beam or girder above at the top?
So that was slide
8.
So yeah, you would need to check the deflection track at the top as well. You're going to have, depending on the condition, you're going to have some higher reactions. Yes.
Okay, so on slide 26, is there a relaxed deflection criterion?
So for the common supply header and Dahu walls, it's going to be that these different deflection criteria. It's going to be for the IBC, that L/240 or 1.5 inches. For the service pressure, L/360 or 1 inch. And then when you're dealing with the extreme pressure, it's a situation where it's an extreme event. You're just designing for strength. You don't need to consider deflection in that case.
Let's see. For installations in high seismic region, slide 38 through 39, what kind of recommendations for lateral bracing?
Okay, so for the structural ceilings, lateral bracing, it would be that same, the same ones at that I showed at the end. So depending on if it's the precast tees, you would have the strut for your lateral bracing, and then if it's either the steel beam or concrete slab, then you can use the 4-way splay wire.
So are there any special considerations for expansion joints due to the higher service wall pressure?
I guess I'm not sure. If it's expansion joints in the wall itself, I mean, they're continuous. I'm not sure I fully understand the question.
Yeah, we can follow up with that later. Do you see a lot of prefabrication with CFMF on these data centers?
I would say for the most part, it's pretty stick built. I've not seen a lot of prefab. For some of the interior, it may be something that would be easier to do. The exterior, you're dealing with stuff that's, it's either metal panel attachment type stuff. It's not a ton that would necessarily lend itself to a lot of prefab, but some of the interior might.
Okay, and then let's see, a couple more just ones. How is the coordination with EOR for the given loads from the equipment going into the building framing?
So, I mean, a lot of the EORs, I would say, have worked on data centers frequently enough that they are pretty good about giving the appropriate loads, especially with the various pressures that you're dealing with as far as wall framing, that they know what they need to give and know how to coordinate it. The structural ceilings, like I said, that's a lot always listed in the spec, or it's always listed somewhere because it's what's required for the end user. So that information is pretty reliably given as well.
Okay, so in the data center projects I have seen, the deflection is significantly larger than the T200 and slotted track movements shown in your details. What would drive the difference in movement requirements between your projects and the ones I've seen?
I mean, so we have had some where we've had to use the deeper leg deflection track than what's shown here. I would say that definitely occurs more on the interior than the exterior. The exterior, it's still typically 3/4, maybe 1 inch of deflection. So you'll have to use, still a deeper deflection track than what you would normally. But on the interiors, we've definitely seen some instances where it's, 1.5 inches up and down. So you have to, use some even larger leg angled deflection track. I think obviously what drives that is just them pushing spans of their structure. So you get some more deflection in the structure overall.
And do you see a need for acoustical treatment, noise and vibration isolation in data center? If so, how are these requirements typically addressed?
I guess I've not necessarily seen anything with that. That's not to say that it's not necessarily a requirement with, some of the sheathing that might be required.
And like last question here, we have an interior wall that's 9 feet high, built within 92mm sill stud, and we need to add an abuse-resistant board up to 4 feet in height. Should we use 25 gauge or 20 gauge studs?
I would have to look at that a little bit more closely. And I would say probably also depend on what the spec requires.
All right. That's the wrap up for our Q&A session. Thank you so much. If we haven't gotten to your questions, we'll love to hear from you. Reach out to us. And thank you for your time. Thank you, Andrew, for the wonderful presentation. Very informative. And thank you for everyone for joining. We'll see you next time. Bye now.
Thank you.